As you want. Maybe I don't. Whatever.
Ladies and gentlemen, welcome to the public session. Basically, Davide Gerosa, University of Milano, Bicocca. He is an expert in gravitational wave astronomy and he's going to talk on our emerging black holes from the stellar collapse for previous mergers. Some years later, for the next hour, please join me in welcoming Davide.
All right. Hi, all. No. It's just a few of us, so we can be informal. Right. So, hi all, and thank for the great organization here and for the award that we received yesterday. So this is going to be the paper. So I got this FSA award, and the title of the paper back in the days was "Are Merging Black Holes Born from Stellar Collapse of Previous Mergers?" And this talk is going to be an updated version on what happened on these topics in the past years or so, right? The paper was from 2017, so there's going to be some 8 years or so of more work on this topic. Okay, so I work on gravitational wave astronomy, and the status of the field is that we've detected about 100 binary black hole mergers. So these are mergers coming from two black holes merging into each other and emitting gravitational waves, which are perturbation in the space-time itself that travel from the source. So there's a lot. There's a lot of echo. Can I get rid of it? Can I get rid of it? It's a small room. Can I get rid of it? It's a small room anyway. It's echo. They're recording. Okay. Maybe. Okay. Yeah, you're right. Let's not screw things. Good. It's on the volume down, maybe? The volume? Okay. There's a lot of echo, and I struggle to. Okay, so I was saying, so we've detected about 100 binary black hole mergers. So these are mergers of two black holes, the most dense objects in the universe. So this is what's happening in our field these days. Right now, we are about, so this is the timeline, but we're about here, right? We're about at 100 detected black holes. They have more that they still need to release. But the field is going to explode in the next few years. So this is some prediction we cooked up a few years ago. And in about 20 years, we're going to get into millions of binary black hole mergers. So this is we're really on the cusp of turning into a big data discipline. Right? So that's what's happening to gravitational wave astronomy. So when you got many events, so you're increasing the statistics of your samples. So very generically, this is going to mean that betas are going to emerge at the population level. So weekly statistical fluctuation are going to become, either die or become more significant. And many events means that we're going to observe a outlier. So things that are in the tails of the distribution are going to start popping up. Okay, so this is the outline of what I kind of want to cover today. So I'll do an introduction on the astrophysics of the problem. So all we need to do, it's a pretty big challenge, by making things like this. So here are, blue and red are the outputs of the two detectors, and this is a physical model that we put through it. From these figures, select the masses and the spins of the black holes and so on, and then inferring where these guys are coming from astrophysically. Then I'll touch base on the statistics that you need to actually do this passage, and then I'll close up with some thoughts on the relativity of the process and how I think that hierarchical, meaning repeated black hole mergers, are promising in this environment, in this context. And this is actually going to be the topic of the paper that got the award, so I ought to mention it today. All right, so before doing any fancy calculation or so on, let's ask ourselves almost a textbook-like question, which is, can black hole binaries really make it, right? So if you take two black holes separated by a orbiting about each other with a semi-major axis with a separation A, like general relativity predicts that the lowest order, the separation goes down according to this differential equation, right? So this is just the flux of gravitational waves that are being dissipated away, and therefore the binary must back react by shrinking the separation a tiny bit. So there's sign here, dAdt, negative dt. Now what you can do with this is play a super simple game, which is, okay, let's extract a time scale out of this. So I'm going to A times dTdA. This thing says the dimension of time, and I'll call it the gravitational wave in spiral time scale. So this guy here is more or less how much time I need before the separation between two black holes can decrease significantly. And what you find is that general relativity predicts that this guy goes as the separation to the fourth power, which is very steep. Now, this has two deep implications for the field. So them is that, again, the power is very steep. So that means that when A is small, TGW is absolutely tiny. So at the very end of the life of binary black holes, their dynamics is entirely dominated by gravitational wave emission. So it's as if the two black holes live in absolute vacuum, right? Everything else, all the complicated astrophysics becomes completely irrelevant because the gravitational wave emission is super strong when the separation is very low. The downside, though, is that, again, this is a steep power. So gravitational wave emission becomes extremely weak when the binaries are very far apart. So we can turn this argument around and compute, okay, let's compute the critical separation, AGW, at which the spiral timescale, so the gravitational wave timescale, is equal to an Hubble time, so the entire lifetime of the universe, 10 to the 10 years. Now, for a typical stellar mass black holes of the kind that we observe, this number is of order 10 to the 10 solar radii, which in astrophysical terms is absolutely tiny, right? If you naively take a binary star, two stars will be at 1,000 solar radii apart, right? So if you naively think that you have a binary star, these stars will form black holes, and the two black holes will form the gravitational wave event that we observe, that's not going to work, like by orders of magnitude. So another way of saying this is that relativity alone cannot explain the events, the gravitational wave events, right? Because you need something else, or some astrophysical way of dissipating energy faster than the gravitational wave, than what gravitational waves can do, at least at large separation, where the typical critical separation is of order of 10 solar radii. So I need astrophysical energy dissipation mechanisms at large separation, and then from that point on, gravitational waves can take over and efficiently drive you to a merger. So this is conceiving plausible astrophysical scenario for this business is the so-called formation channel problem in gravitational wave astronomy, which is a major industry in the field. So let me simplify to the bones with these silly diagrams here. You can imagine having two stars, like an old couple or so, asking each other, have we been together for so long? So there's mainly two ways of forming binary black holes. One is from a binary star. So you got two stars, one star collapses, forms a black hole. You have this intermediate phase of star and black hole. These are the star collapses, forms a black hole, and that's the binary that you see. We will see in a minute this as challenging to make this work. Or you can have a completely different scenario where you have two stars that don't know anything about each other. They separately collapse and form black holes. And when the two objects are already black holes, they meet and form a binary black hole that then you eventually detect in gravitational waves. Now, the key difference here is that these two black holes here, they've been knowing each other throughout, so for mega years, for their entire lives. While here, they just met very recently. There are challenges to make any of these scenarios actually work, and I have a slide on each of them just to. So, by the way, there are hundreds, not thousands of papers published on this business, right? So let me just quickly introduce this. So in the first case, where you have two stars that collapse, so a binary star that becomes a binary black hole, typical formation channels works as follows. So you start with two stars on the main sequence, so that's where stars spend most of their lifetime. One star, in the late phase of stellar evolution, stars tend to expand. So one star starts to expand and drops mass onto the secondary star. Then the first star needs to collapse and form a black hole. So going through a supernova process. Now, a supernova is a pretty disruptive event. It's a violent explosion. So first challenge here that needs to happen for this to be viable is that after the supernova explosion, the object is still a binary, so that you don't disrupt the binary entirely. Then, stellar astrophysicists think that that's actually the key aspect is what happens right here. So here we have a black hole and an extended star. So this star now needs to expand into supergiant, and the envelope of the supergiant needs to engulf the binary itself. So it needs to be bigger than the binary separation itself. So in this case, you have an hydrogen envelope with a black hole inside, which is the product of the previous supernova, and then an helium core, which is the core of the star that is expanding. So you have two compact or semi-compact objects orbiting in a sea of hydrogen, and the net effect is that you dissipate the binding energy of the envelope into the orbital energy of the binary. So the net effect is that the separation here shrinks by a lot, and people that do this calculation think that you can actually decrease the binary separation by up to 3 orders of magnitude. So that's the key thing that, one of the things that needs to happen for this scenario to be viable. Now then, let's go on. Now this binary is much tighter binary, so 3,240 or so solar radii. Then this guy needs to collapse, form another black hole, and this is ultimately the binary that you observe in gravitational waves, if all of it. Now, a completely different way of it is via stellar dynamics in dense environment, namely clusters. Now, in dense stellar clusters, take globular clusters outside of our Milky Way, what happens are frequent three-body interactions. So in a three-body interaction, this is a picture from a seminal paper. So the three-body problem in Newtonian gravity is chaotic. So it's not, you can't predict it, analytically one-to-one, but you can make statistical arguments based on this. And so what typically tends to happen in a three-body scattering is that you have a binary, so 1 and 2. So you have a binary that comes in and it encounters another single object, say another single black hole. No, there's some very complicated dynamics going on at the encounter, but the net effect is that 2 black holes escape as a binary and 1 black hole is ejected as a single. Now, these are not the same guys as they started before, right? So this was 1 and 2 meeting 3, and now in this specific experiment is 1 and 3 and 2 goes away. But statistically speaking, the object that leaves takes away more energy than what the object, the interloper before brought in. So the net effect is that this binary that escapes is tighter than the binaries that came in. So it's effectively a way to reduce binary separations, right? Now, dynamicists that do these actual calculations, so this is a specific, example of this, and if you do it thousands of times, hundreds of times, right, by a very complicated three-body interactions and so on, people that do this calculation claim they can actually predict a decent black hole merger rate. So this is a different way of forming binary black holes that actually relies on stellar scattering more than stellar evolution. More recently, there has been another, so if you want a third player in the game, which is these ideas of forming black holes in the disk of AGNs. So the scenario here would be large reservoirs of gas, like those that we see in the center of many active galaxies. So the y dot here, so this is a simulation. The y dot here is actually a supermassive black hole of, say, 10 to the 6 solar masses, like those that populate our Milky Way, say. So in some active galaxies, there's a large gaseous disk, and you can have perturbers inside. So these are small black holes, 10 solar mass black holes, like those that we see in LIGO. So this phenomenon is actually called planetary migration because it's the very same physics that the planet people use to explain why big planets like those of the mass of Jupiter are very close to their central star in some exoplanet systems. So what can happen, you have these two objects here, they excite density waves in the disk, and the gravitational interaction in these density waves actually acts towards decreasing the binary separation. And the reason why I got interested into this is the debated but probable occurrence of something called migration, which are location in the disk where black hole outside would migrate inwards and black hole inside would migrate outwards. So that would be a natural point for multiple black holes to meet and eventually merge. And I'll touch base on migration traps in a minute again. Okay, so in all this, not really chaos, but extreme creativity of different models and so on, now the obvious question becomes, well, can we tell them apart, right? Can we figuring out from the things that we measure in gravitational waves, which of these channels is dominant at least or so. And so this is what we thought in 2017-ish, more or less, where I wrote the paper that got the award. And we were extremely optimistic back in the days, right? So paper claiming that, with 100 events, we're surely gonna distinguish, and just using the masses that we measure and the rates, so how many, we're surely gonna distinguish these population models. We're even going to measure eccentricities, and everything is going to be beautiful. I did back in the days a lot of work on showing, well, ideally, how not even you can distinguish the channels, but by spin measurements, you can actually tell where the supernova take place, tidal interaction, and mass transfer in stars, and so on. Now, this was back in 2017, and it turns out that I like to show these slides because it turns out we were extremely optimistic, right? In reality, life is way harder than what we thought. So the first gravitational wave events are now 10 years old, so September 2015. And in 10 years of gravitational wave astronomy, we have not solved the formation channel problem, and we are far from it, actually. There are several reasons, but there are many unknown processes. So the astrophysics problem here is dirty. There's intrinsic degeneracies in our data and the things that we measure. So yeah, selection effects are a big problem. So not all black holes are equally easy to observe. So it's crucial to deconvolve the filter that our detector is imposing for data to actually reconstruct the astrophysical population. The statistical problem turns out to be challenging, or at least we know how to write down, and I'll write it down in a minute, the likelihood of the problem, so how to trace the stats, but then actually the implementation can get tricky very, very quickly. And well, my theoretical astrophysics strengths are actually creative, and the prediction change over time. This is more a sociological problem, I guess. All right, so we need to extract this information. We're interested in all this astrophysics we need to extract this information from the gravitational wave data. And so to zeroth order, there are like 3 levels of gravitational wave data analysis, like a cake here. So the first level, down at the bottom, is that of the searches. So the LIGO events are like 0.1 second long, so they're very short and concentrated. So LIGO takes a year of data, and the events that we care about are 0.2 seconds or so. So the first challenge is the search problem. So find the interesting, second or so, or millisecond in a year of crap. So that's the first thing that one needs to do, right? We're interested in about 100 seconds, so 100 events in 3 years of data, right? So that's the first deep challenge. It's not my core expertise, but that's really at the bottom of what we do. Then once you've identified that 1 second of interesting data strain, then you want to run, we call it parameter estimation on it, which is for that specific stretch of data, analyze it deeply. So necessarily this first stage is kind of coarse, right? You kind of want to find the interesting data segment, not really characterize it. Then because you don't care about characterizing the whole thing, you want to characterize what's interesting. So from there, do parameter estimation, meaning run sophisticated Bayesian tools to find the masses and the spins and the distance and the redshift and so on of the black holes. Now, and this is the second level of the cake, then the top level would be the many events that you've detected together. And this is actually my core expertise here, which is given, now that I've measured 100 masses, say, I have 100 measurements, all of them with their posterior distribution, so all of them which are affected by statistical uncertainties and affected by selection biases, because we know they're not all equally good to see. What can I say? How can I put this thing together and infer the overall population of black holes in the universe, which is what I then actually want to compare with the astrophysics. And if you want, this is the top layer of the wedding cake here. All right, so let me write down the likelihood of the problem. So this is the stats that we are facing. Right, so, okay, in this notation, theta are the single event parameters, so say the masses, the spin, the redshift, or so on of the single black holes. Lambda are the population parameters, meaning the things that keeps the black hole together. Say it could be which of the supernova processes or whatever. Easier, it could be, say your masses is a power law, that would be the spectral index of that power law. Now, the generating process of your data, meaning the likelihood, is as follows. And let's try to unpack it. It looks hard, but it's really not that much. So what we care about is this guy. So I care about the probability of my astrophysics, lambda, given all the data that I've collected. Now, this data that I've collected is separated into chunks of the individual events, di, which are, in this approximation, and for LIGO is an excellent approximation, it's a good approximation to say that the events are independent. So there's no overlap between events. So I could just take a product of the many events. What I have inside here is the likelihood of the individual events, so the probability of getting my stretch of data given the properties of that single one black hole, weighted by, this is like a prior, weighted by the probability of measuring the of producing the black holes in a given astrophysical environment. So this is astrophysics to single parameter to data, and the overall thing is data to astrophysics. That makes sense, right? Now there's a crucial bit here, which is the sigma factor here, that takes into account selection effects. And it goes as follows. So first of all, there's a minus here, and now I'll say in a minute why that is. It goes as so this is the detection probability. So the probability of detecting a black hole with a given parameter weighted by my astrophysical population. Now, an intuitive way of seeing this is the follow. So you can think of it as this way. Right? So suppose that you measure one black hole of 50 solar masses and one of 5 solar masses. You know your detector is 10 times less sensitive to black holes of 5 solar masses. So observing black holes of 5 solar masses is 10 times harder, right? Now, if you see 1 and 1, naively you would say, oh, well, I've seen 1 and 1, so black holes of 5 and 50 solar masses are equally likely in the universe. That would be a very wrong statement, because the fact that the 5 solar mass black holes are 10 times harder to see, it actually means that in the universe there are 10 times more, but it's harder to see, and so I've seen only 1. So my inference should tell me that actually the 5 solar mass black holes are way, way more probable. So there's way, way more of them in the universe, but I'm only observing a small fraction of them. So, and this is this minus n here, right? The more events you see, the more you have to reweight your population, your inference by selection effects. This is the Malmquist bias in other astrophysical fields. It's really the same thing. Right, so one key aspect here is the population, right? So you need to assume a population and measure its parameter, right? Now that the art become, and there's a vast amount of literature here, what population do you actually select here? And there are mainly two things you can actually do, right? So option one, which is actually still state of the art, I want to say, because of its appealing simplicity, is to use simple parameterized functional form, Gaussians, power laws, and things like this, right? So this, it's nice because they're simple and encode some physical intuition without getting lost into details. Now that said, these physical intuition are also hard-coded in this functional form that you choose. So more recently, people, including myself, have been exploring other ideas of actually how to model the gravitational wave population. And you can do two ways, right? So you can go the non-parametric direction. So this would be a data-driven approach in the machine learning framework, right? Where you actually assume almost nothing about the shape of the population and ask your data to not only measure the parameter of a given shape that you impose, but also measuring the shape itself, right? So this would be, data-driven, machine learning-driven approaches. You can do the completely other way, which is do a direct fit to astrophysical simulation. So very strongly model dependent, go to your astrophysics friend, trust their population and measure the parameters of those population using gravitational wave events. Now, this would be, so it's much closer to the astrophysics, right? Because you're actually grabbing, so at least the way we've implemented it is to use state-of-the-art astrophysical simulation that seems beautiful, but you're also inheriting their systematics biases and errors. So I don't know. Yeah, and I think exploring all options and seeing what's solid, what's robust about this, it's actually the way forward. Okay, so this is the state of the art. So the population of black holes that was measured by current LIGO Virgo events. So GWTC3 is the latest data set of events. And what they found is, so this is the distribution of primary masses. Only look at the blue curve here. What they find is that there's a lot of black holes at about 10 solar masses. Now, this peak here, note what I was saying before, is entirely dominated by selection effects. There are actually very few events measured here, but they're so hard to see that we infer that there's a lot. And this is in log scale, so there's order of magnitude more here. Then the overall trend is that of a power law distribution, notably with an excess at about 35 or so solar masses, which is generating a lot of interest or so to figuring out why black holes actually preferentially pile up at about 10 solar masses. 35 solar masses. Now, this is the distribution of their mass ratio. So 1 means that the two black holes are equal to each other. 0 means that, well, they have a test particle into a black hole. And this goes up, meaning there's a preference for black holes to pick with similar black holes. So big black holes tend to go with other big black holes. This is the distribution of spins of the black holes in units such that 1 is maximally spinning, meaning there are theoretical problems to go above 1, and 0 means the black holes are non-rotating at all. And the gravitational wave event seems to prefer somewhat lowish spin of about 0.2 or so on. So it seems there seems to be nothing around here so far, at least. Okay, so this is the state of the art. One other super interesting thing that came out of recent data analysis results, so this is really review material, is correlations between parameters. And the one widely expected thing is that the mass spectrum should evolve with redshift. So the black holes at higher redshift, so if you look farther away in farther ahead in the universe, black holes should be more massive. This is widely astrophysics, but actually not yet detected in the data. It's a very difficult measurement. What was detected instead is something kind of bizarre, which is an intriguing correlation between the mass ratio of the black hole and the spins of black holes. So it turns out that when the mass ratio is low, so black holes pair up with different, so one black hole with a smaller black hole, the spins of black holes tend to be higher. And this is extremely puzzling because there's basically no astrophysical model that can predict this. And I actually asked the author about this, and he replied, I tried very hard to kill this correlation, but actually couldn't. So this was really completely serendipitous. And it was confirmed by, well, several people, including ourselves, and it seems to be a really solid feature in the data that is so far, well, unexplained. I have a model that tries to explain it, but it's not successful at all. All right, so in terms of astrophysics, one key prediction that actually brings me to the topic of repeated mergers is that of gaps in the mass spectrum. So this plot here, this is just stellar evolution, right? Forget about gravitation, this is just stars. So on the x-axis here, the zero H-band sequence, so the mass of stars. And this is on the y-axis is the remnant that they produce when they end their lives. And the first family of objects here, so a star of 20 solar masses will produce an object of 1.4-ish solar masses. Those are the neutron stars that we all know and love. Then there seems to be nothing here, though this is debatable. Then there's another family of objects here between 10-ish, with 5, whatever, to 50, 60 solar masses. Those are the black holes that we like and love and measure. And then there seems to be nothing here again. So, and then more black holes down up here. Now, this nothing is so-called the upper mass gap or the pair instability mass gap, and it's actually extremely precious. So let me go a tiny bit into the physics of this. So this is another plot from some simulations of collapsing stars. So now on the x-axis here, this is the CO, is the carbon-oxygen, the mass of the carbon-oxygen core of the star, and this is the black hole mass that they leave behind past the supernova explosion. And down here, everything is fine. It's kind of linear, right? The bigger the star, the bigger the black hole. This seems fair. Now, something interesting happens here, which is when the mass of the carbon-oxygen core becomes too large, then you don't produce big black holes anymore, but the black hole mass plummets down. What's happening here is an instability in the core of massive stars, and it kind of works as follows. So at these masses here, the temperature in the core becomes large enough such that photons spontaneously decay into electron-positron pairs. Now, if you remove, this way you remove photons from, meaning you're removing radiation pressure. If you remove radiation pressure, the core of the star will contract, the temperature will go up. If the temperature goes up, you produce more pairs, and that's gonna produce more electron-positron and one other. So it's an unstable behavior. All the way to, and that's what happens here at the peak, all the way to reaching the temperature of oxygen ignition. So you ignite the oxygen, which lights up much like igniting a fire or so. And what happens here is that basically the entire star is gone and you produce no black hole. So you explode, everything explodes without leaving a remnant. Now, if talk about this with my astrophysics friend, they tell me that, black hole should be forbidden for masses that are much larger or twiggle or so, that depends on the models, but about 50 solar masses. So if you see black holes larger than 50 solar masses, it's kind of hard to do them via stellar collapse. So that's the key prediction, and something I explored at length, given these results, is whether we can bypass stars entirely and use black holes. And it's actually the topic of the paper that got the award. So that was 2017, and we were thinking about all this business, And we wrote this paper, are merging black holes born from stellar collapse or previous mergers? And what basically we are saying here is that, well, if you do measure in the future a black hole of masses much larger than 50 solar masses, maybe that doesn't come from stars, but that comes from previous mergers. So there were another generation, an older generation of black holes that form smaller black holes. Then those two black holes meet, and that's the black hole that I observed. That would naturally evade the pair instability supernova. And then we point out how they are interesting spin signatures in this kind of event. And that's actually the main result of this paper. So this was 2019, and then this was 2017, sorry. And then in 2019, this thing happened, which is, well, you guessed it, but a black hole with extremely confident detection of two black holes, so a merger of two black holes with 65 and 85 solar masses, which, well, was widely believed to be impossible before this. And actually, this is old news. Interesting day to give this talk today, but right today, the LIGO collaboration, they've released an event. I still haven't read the paper, but it came out this morning with a black hole of 100 and 130 solar masses. So that's pretty exciting news, and I can't wait to see where this is going. But so let me proceed with 1905, with 1905-21. So the idea that we had back in the days was the following, right? So suppose you have some stars here, they collapse, form first generation black hole, and that's the event that you see. So these two masses are limited by this pair instability limit of 50 solar masses. What if instead you got stars here, they form black holes. Now these two black holes are limited by the pair instability supernova, say 50 plus 50. Now this guy will be 80 solar masses, that's fine. And then these two black holes meet, and this is the event that I observe, right? Now, this guy here, if this gravitational wave signal reaches LIGO, it won't be bound by the pair instability limit, because I'm not using stars, I'm using previous black holes. And we pointed out how this could be an orthogonal but somewhat complementary direction to the usual isolated star versus cluster debate, because this relies on the relativity of mergers, but of course you do need some form of dynamical environment to actually assemble black hole together. So I like the complementarity of approaches here. And then the other crucial signature of this, which was, well, then we asked, well, okay, you see a big black holes, but, you know, is there something unique about this repeated mergers idea? And the secret is in the spin, this magic number thing of 0.7. Now, this has to do with the general relativistic effect called the orbital N gap. Now, when you merge two black holes, you got the orbital angular momentum of the binary before the merger, and then the two spins, and then by momentum conservation, these things become the spin of the final black hole past the merger. Now, the orbital N gap effect works as follows. So if you have the spins that are aligned to the orbital angular momentum like this, the binary orbits a bit more. So there are a few more orbits and then the merger. So they hang up, right? That's how these people called it. Now, what that means is that, so if there are a few more orbits, the orbital angular momentum is a bit lower. So L is a bit shorter, the L arrow here is a bit shorter, but you have to do L plus S1 plus S2. On the other hand, if the spins are anti-aligned, they plunge from afar. The black holes plunge from afar, meaning that you have to do L minus S1 minus S2, but L is longer because there are fewer orbits in the binary before merger. So there are two effects here that kind of counterbalance each other, such that more or less whatever you do, the spin of the final black hole is closely peaked at 0.7. This is a specific realization using numerical relativity results, actually, where we started from a first generation of black holes of spins that are flat, like completely uninformative, and already by the second generation, so look at this red line, the distribution of spins closely peaks at 0.7. So the idea that we put forward is, well, if you see a black hole that is very high masses, so you can do it by stars, and it has large spins, this repeated mergers idea actually becomes extremely, extremely promising. And actually, when we put this out, then there was an explosion of predictions, right? So this is a more accurate description of this same thing I described. So blue here is a distribution of black hole consistent with what we measure. So this is extracted from the data. And here we computed their second generation black hole. So what would happen if they would merge again? And as you see, the masses go up. So this is mass. The masses go up, arguably above 50, or at least there's a tail above 50. And the spin, so chi, they go from this to this super sharp peak. And well, people started exploring all these things, right? So we point out there's a peculiar spin distribution at 0.7. There's a catch here, which is that when two black holes merge, the final remnant actually recoils away by linear momentum conservation, and you cannot do it too much, otherwise you kick the black holes out of the clusters. This turns out to be frequent in this AGN disk that I talked about. Is now a leading explanation for this 1905-21 event, and even more so, I would say, for the event that was released today. Statistical analysis pointed out that there might be several of these repeated events in the LIGO catalog, and there might even be responsible for some of the correlations that I was hinting at before. And so we collected all these thoughts a few years ago in a popular review where we summarized all this body of knowledge that came out of the idea of thinking about gravitational wave events as repeated mergers. So yeah, this is a plot from their review where, you know, there are many, so these great things are the many astrophysical ideas that we have to form black holes. And if you then classify them into whether they can produce first generation or hierarchical mergers, you find what kind of happens is that only a subset of these with different efficiencies, so dashed lines here means yes, but not much, only a subset of these can actually contribute to this subpopulation of black holes. That means that identifying this subpopulation is actually a leverage to actually figuring out where the black holes are coming from in the broader astrophysics context. And right, so this is, I really like this figure. This was from a paper a few years later, because you know that every theoretical physicist, if you have an idea, you want to try and kill your own idea and see if you can, right? So we started thinking, okay, what black holes do I need for that not to be hierarchical mergers? So can I kill my own idea? So, and what we came up with is a variety of models. So we tried to vary more or less everything that we could. And well, something that is obvious now, but it wasn't obvious is that it's almost empty area down here, right? So if you see a black hole which has a large mass but low spin, that's kind of hard to do with hierarchical mergers. And that's, well, now it's obvious after this 0.7 spin thing that I just said, but at the time it wasn't. So observing a black hole right here, say 100 solar masses spins of 0.1, that would be extremely hard, if not impossible, to do it via this way, which means you need something else, and you need to be more creative there. To put a black hole there, you really need some more astro reasons, which are not merger based. And people have proposed low carbon oxygen reaction rate, weakening the stellar wind, playing with star rotation, collisions between star accretion, more massive stars in the early universe, and so on. So, but this would a black hole. So my prediction is that a future detection here will kill my own idea. Okay, so before I'm almost done, but just want to flesh out these results. That was done by a graduate student with me, Matt Mold, at the time, who's now a postdoc, where we tried, okay, what if, can I actually extract these hierarchical merger subpopulation apart from the data? And well, you quickly meet a very technical issue here, which is that even if you start from an easy population, say power laws and Gaussians and so on, as soon as you make it hierarchical, so you mix it with their own merger product, the result becomes non-analytic. And for all the likelihood that I said above, you need to evaluate the likelihood many times. And if each likelihood evaluation is the result of a simulation, you're quickly out of luck and things are never going to work. So we use this hierarchical merger idea to actually prototype a deep learning pipeline to extract and be flexible about the population of sources. So we constructed a neural network, which is in turn based on KDEs, which takes into account both selection effects modeling and this hierarchical Bayesian analysis to do the population inference. And so details apart, these are our results. So this is the distribution of masses fitted via this model for either of the two masses of the black holes. But now we distinguish between a subpopulation of hierarchical mergers. So if we now down select and only show the first generation masses, the purple line here, the fit does what you should expect, right? So the low mass n is basically captured by the first generation black hole, and this high mass n and higher generation takes care of fitting the 50, 60, and 70 solar masses black holes. And this tail is entirely dominated by that one event, GW 1905 21. Okay, so again, some more details on this, but this is our full pipeline for this business. So you want to start from some population parameters, that's your assumption on the astrophysics, simulate some events, so some mock catalogs, simulate your source parameter, these are going to be your observable, and then you're going to go down three ways here. So this way is used to infer the merger generations, so the branching fraction, so how many black holes you have in each black holes, and there's a deep learning pipeline down here. Then you want to estimate selection effects, which is so critical and needs to be done very accurately, which is another neural network. And now this thing instead simulates the actual source population, so PPOP. You put all these three events together with the data, of course, they need to come in and extract the astrophysics that I was flashing before, admittedly very, very quickly. Okay, so just to flesh out some results that came out of this hierarchical mergers idea, this is something I worked on with another student, a master student at the time, he's now a PhD student in Germany, Alessandro Santini, where so I asked him, okay, please look into this correlation because this is really puzzling. So this was the result that I flashed out before of LIGO observing a correlation between the spin of the black hole and the mass ratio. So uneven masses being higher spins. And we started thinking about it in this hierarchical mergers idea. And well, you kind of works, but kind of doesn't. And so down here, of course, if you pair up generations of black holes, you can imagine a second generation black hole being paired up by a first generation black hole. This would explain how you go down in mass ratio. And for this spin 0.7 thing that I was saying before, this should also pump up the spin. So you actually expect things to go here, right? So this state here could be black holes from other black holes. The one up here could be the normal black holes from stars. But then you also meet the problem that there's nothing here. And negative in this variable here, negative means large but counter-aligned spins. And there's really nothing that should prevent you from going here. So it was really puzzling how, the data seems to go into this region, but not here. And what we realized is that you could actually make this playing with the symmetry of the environment, right? So this is a case. So these are admittedly a very toy model size, but so these would be isolated stars, isolated binaries, so binaries that come from stars, and you go into this gray thing. These would be hierarchical mergers in spherically symmetric environment where the directions are all randomized, so you equally populate either the minus or the plus sign in this plot. And then let's look at all the way at this. These are black holes hitting in AGN disks, the third scenario that I was saying at before. And if you have an AGN disk, you have a preferential direction, that's the orbital angular momentum of the disk. And that preferential direction could maybe be transferred to the events that you see. And that actually precisely goes in the direction of killing this left wing here and actually only leaving you with this right wing. And we did some more stuff, but if you construct a mixture of the gray model and the red model, it gives a somewhat decent fit. Not great though, so I think there's far more to be done and discovered here, but maybe the symmetry of the environment actually plays a role in all this business. So yeah, I'd just like to flesh out this result by students. Okay, so this was kind of the end of my talk. There's some time for questions now, but more is happening very, very soon in my field. So right now, LIGO has done 3 observing run, nickname 01, 02, 03. We are actually, so that's the data that they've released. They've actually have more data in their pockets that haven't been fully analyzed and cleaned yet, but there's going to be at least another 100 of events. So we've detected about twice as many things that those that are being publicly released. So, and the next data release is due at the end of August. So in a bit more than a month or so, our data set is going to double in size, and it's going to go to the millions in 20 years. Large statistics, I'll say again what I said at the beginning, increasing the number of events means details emerging at the population level. So all this idea of extract subpopulations from the set that you've seen and whatever, if you have a population that takes about 10% of the events, well, if you double in size, it's going to be twice as much information there, right? And then many events means rare outliers. And again, let me flesh out the one event that was released today. So it's on the archive right now today, where they have an event of more than 100 solar masses, which is absolutely spectacular. And I still need to digest what it means for all these hierarchical merger. And yeah, with this, that's all. Again, thanks for the award, and thanks to all collaborators and students actually that work with me on all these things over the years. Oh, large, right? So we're about 10%. There's a few. So okay, here I need to go into some details. So need to distinguish what we actually mean by spin. Actually, in this, where is it? So say in this plot here, oh, actually I have the expression here. Let me go back. Let me go here. Right. So okay. So in this expression here, chi1 and chi2 are the spins of the individual black holes, and thetas are the direction of the black hole, of the spin of the black hole measured from the orbital angular momentum. Actually, the thing that we measure best is this guy here, chi effective, which is a combination of the two. And the reason is that is the number that enters at lowest order in the gravitational wave phase. So we have somewhat decent measurements, 10%, something like this. These are the number we're talking about on this thing, but disentangling, so breaking the degeneracy here, it's considerably harder. Now, the secret here, the promise here, it's really combining multiple events. So what happens here in this plot, this is the population of spin. So that's what happens if you combine 100 spin measurements, or 200 if you have two black holes times 100 events, right? And I don't know what's the width of this thing, is about 0.2 or so on a scale from 0 to 1. So it's a difficult measurement, but nonetheless, we need to go after this, because after all, it's the other observable that we have. So black objects, they only have a mass and a spin. Past the mass, we got to measure the spin. So it's the other thing that we can measure. Yes. Oh, okay. So this paper here. Let me go. Where is it? Let me go here. So this paper here was. So the goal here was. So back in 2022 was twofold. So first was to prototype all this idea of interpolating population with neural networks, and then was to investigate So the astrophysical take was to investigate hierarchical formation channels. So ideally, you want to do it with actual core astrophysical simulations, right? You need order of 10 to the 4 of them. That's the answer that you want. We're able to do it because these are toy simulations where I have an easy first generation population, and all I need to simulate is their merger product, for which there are fast interpolant existing already. If you were to do it with actual population synthesis, so actual astrophysical simulation, we have done it in another paper with it was much more limited study, because we could only explore one parameter in these many population models. But yeah, the order is 10 to the 4, and actually other groups more than my own. I kind of moved on from this topic, but other groups are now aggressively pushing the construction of large data set to actually feed these guys. Well, let's see. But we prototyped it back in the days some years ago for these hierarchical mergers idea, and it was one of the first in this business, at least. Now there are more advanced pipeline actually that do the same, that pursue the same idea.
One is not that show they are mostly towards lowest. So is a hint that are you agree? It is a hint that they are first generation, right?
Mostly, yes. So, but that's something that's absolutely very true. The role, I mean, in my view, the role of these hierarchical mergers idea is that of capturing a small subpopulation of sources, maybe 1 in 100 or so, right? So to explain the very, very high mass events. It's far more probable, and all astrophysical models agree, to have first generation black holes. So the bulk of the population is going to be from stars. And then maybe a few outliers from this hierarchy. So you have to see it as a way to explain the very few, very high mass outliers, more than, not really the bulk of the population.
So, and another thing you said was the disk that causing the spin alignment. So if you have another distant galaxies with different angular momentum, does that cancel? Yeah. So in this,
Where was it? You meant this one? This is this what you meant?
yeah. So if they are some black hole and some black hole another environment.
Oh, the scales are very different. So galaxies are very far apart. So the scale is very different, right? So they're not really going to interact. It's a completely different scale problem. Thanks. Thank you.